Greetings, everyone. Let's continue our discussion of logarithms and their properties, specifically some of the advanced properties this time. Okay? What we're going to do in this section is learn all of the different tools that we'll need in the next section to do all of the solving that is required. Okay? So properties of logarithms, we've already gone over a few of these, right? Log base anything of 0. You can't do the log of 0. It's undefined, right? Log base anything of 1 is 0. And that's because anything to the 0 power is 1. The log base anything of itself is 1 because anything to the 1 power is itself. And then we had the change of base formula, right? I can take any logarithm and rewrite it as two logarithms that have the same base. I usually pick ln just because it's less writing, and we do a lot of ln calculations later on anyway. Okay, now to advance the properties a little further, the connection between logarithms and exponentials was discussed last time, them being inverses. So now let's look at the algebraic side of that. If I were to perform a logarithm onto something that already had an exponent, if the bases of the logarithm and the exponential are the same, then those are inverse operations that would undo each other. Notice the p is the only thing left after they wipe out. Vice versa, if I were to enact a base and have that base raised to a power that is a logarithm of the same base, right? The logarithm is in the power and its base is the same as the big base. Those also are inverse operations that would wipe out, leaving just the argument of the logarithm behind. Okay? So here's a quick example of this one. Notice I can rewrite 25 in the log base 5 of 25 as 5 squared. And since these bases are the same, I can essentially wipe those, leaving me with a 2. But you already knew this answer was 2, right? What power turns 5 into 25? That would be 2. So you already knew that connection there. And here, just anytime this happens, and this very often is used in solving just to quickly get rid of logarithms. Bases tend to be felt as the opposite of the logarithm. The base itself is not, it's the way it's being used, right? If a logarithm is used as an exponent, right? Don't forget, logarithms calculate exponents. So then if you take that logarithm and use him as an exponent, right? It's like a natural fit. And then also, if the base is the same as the one being discussed, forget about it. All done. Said and gone. Okay, so those are the simple properties of logarithms. Here are the big three. These are the ones that we're going to be using with pretty much any branch of math, and how logarithms are different than other operations. Okay, we have a product property, a quotient property, and a power property of logarithms. And basically, it's exactly the things that we're talking about here. If I have a product in a logarithm, then it came from the addition of two logarithms that have the same base. Okay? And you already knew this property, but you've probably seen it another way. Anytime you have something where you're multiplying bases that are the same, for example, x squared times x to the third, you add the exponents, right? This is the same property. I'm adding two exponents, right? Logarithms are exponents. And if I add those two, then it should result in something with a multiplication, like that, okay? And of course, the quotient is the same kind of connection. Anytime you subtract exponents, it comes from some sort of division. But these two properties are sort of like a reversed feeling of what you've used them as before, okay? What's going to happen is I'm going to have to use these properties either in the forward or backward direction, depending on if I want to spread something out or bring it all back together, okay? So if I have two logarithms that are separate, but I don't want them separate and I need to squish them back together, I can do that as long as their bases are the same, and adding would then turn into the multiplication of the two arguments. Vice versa, if I have two logarithms that are subtracted and I want to squish them together, then the subtraction would lead to a division of the x and y arguments. Okay? So these two right here bring out what I call the accordion actions, right? In and out, like an accordion, like that, right? Okay, and then the mortar between the bricks, the power property of logarithms. Logarithms already do amazing things with exponents. This is the epitome of it, okay? This property, notice it looks a lot like this one over here. Major difference, this x is not the same base as this a, where it is over here. So here these are inverse operations because they're the same base. Here they're not. However, this property still allows me to do something. I can take any exponent that's inside of a logarithm already. So that's an exponent inside of an exponent. You've seen that before too. When you have a power raised to another power, you multiply them. Same thing. I have a power inside of another power, an exponent inside of another exponent. What happens? I multiply them, right? The lingo is I bring the p out to multiply. But really what's happening is I'm seeing two exponents and I'm multiplying them together, okay? And you know, some examples that go along with it. As long as the logarithms have the same base, right here, right? I'm adding the two logarithms. 5 times 3 just gives me the log base 7 of 15. And you can check that one in your calculator, right? Do this calculation on one side and then do that calculation separately. You'll see that they give you the same number, okay? Same thing here. In your calculator, hit ln4 minus ln3. Hit enter. And then also hit ln of 4 divided by 3. You'll see that they give you the same value. Lastly, log of 16, right? That's a base 10, but punch it in your calculator, log 16. 16 is also 4 squared, and according to this property, I should be able to bounce the 2 and multiply it in the front. So in your calculator, hit 2 times log of 4, and you'll notice it's the same answer as the log of 16. Let's just go through some structural examples real quick of the rules themselves, okay? So what I've got here is I've got two logarithms, and the instructions are going to say condense or simplify in some sort of way like that, okay? Later on in equations, you'll just know when you have to do that because you have two logarithms and you want only one logarithm, right? So here, what I want to do is I want to pay attention to the fact that the 2 and the 5 are in front of my logs, and notice my subtraction rule doesn't allow for that. There's no numbers in front of those logarithms. Well, that's where the power rule comes in. I can do this in either direction, right? If there's an exponent in there, I can peel it out to the front, or if there's a number in front of a logarithm, I can bring it back in as a power. So right here, both of these, I can rewrite them. This is going to be the log of a squared minus the log of b to the 5th. Now it looks like the quotient property, in which case I can just say the log of a squared divided by b to the 5th. Okay? All right, next, the log of x plus 1/3 log of y. Well, again, the 1/3 needs to be brought in as an exponent. So that's going to be log of x plus the log of y to the 1/3. Now remember what we know about fraction powers. They're really radicals in disguise, right? So I'm going to actually rewrite this as the 1 power and 1/3 root of y. But I'm going to do it in the next step. So since I'm adding two logarithms, right, I can use the product property. I can merge these together. I'm going to get the log of x times the 1/3 root of y, like that. Okay? Now, this last one right here is more for the structure than anything else. Log of a plus log of b minus log of c minus log of d. Okay? Now I know what you're thinking. I should multiply, divide, divide. Don't think of it that way, right? Whenever I look at one of these problems, I don't see product property, quotient property, let's do them separately. No, no, no. These are actually the same property, right? They're the same property in two different manifestations there. And remember, what's happening is, with a subtraction, I'm really getting a negative exponent for that second one. Remember, negative exponents put things in denominators, they divide them, right? So that's really what's happening here. It's all these same properties. Both of these two are. But whenever you have a negative logarithm, it's a negative exponent, things get put in denominators, right? So instead of doing each one separately here, think of it that way. The logarithm on the A is positive, the logarithm on the B is positive, the logarithm on the C is negative, and the logarithm on the D is negative. So to just cut to the chase, I'm going to merge these into a single logarithm, log of, and what I've got is AB over CD. See what happened? Yes, C and D are multiplied even though there's a subtraction, but that's the way it should be. They're both negative. Remember, things are the same sign. They actually are adding, okay? But again, above and beyond that, the logarithms themselves dictate the locations of these. A and B are both positive logarithms. They're in the numerator. C and D are both negative logarithms, so C and D are in the denominator. Let's finish up with doing these 6 examples of expanding and contracting, or actually rather contracting and then expanding, using these advanced logarithm properties. Okay, so let's start here at the top. I'm going to combine these two logarithms. Again, notice all of the logarithms in each problem, they all have the same base. That's important. Okay, so I have 2 ln x plus 3/4 ln x plus 5. Now you can really just sort of do this all in one. Remember, the numbers in front have to be brought in as exponents, right? They have to be brought in to make the other rules work. And I notice that I have 2 logarithms that are both positive, right? So they're both going to be numerator. Okay, so I'm going to bring the powers in, and I'm going to make them one logarithm. This is going to be the ln of x squared, right? Bringing the 2 in, times x plus 5. Let's make this a bracket just so we don't get mixed up. To the 3/4 power. Now, in some cases, they may want you to rewrite the 3/4 power. And don't forget what that means is a 3 power with a 4 root. Okay? It just depends. So you're completely fine with rewriting it this way. In some cases, it may be better to leave it in the top format. It just depends on what math you're doing and what application is for. Okay, next. I've got 2 logarithms to combine again. And the first thing I notice is that I've got a positive one and a negative one. So I'm going to have something in a numerator and something in a denominator, right? They're both log base 10. So I'll write that, log base 10 of, and I know I've got this structure going on. Okay, well, in the top, the 4 was supposed to come in as a power, so I can just write x minus 3 to the 4th, right? That's one object. And next, I just have x in the negative logarithm, so he's in the bottom. And there you have it. Okay, now what about this last one? The last one here, we're going to talk about bringing 3 of these together, right? Smashing these 3 together. So I know I'm getting one logarithm, base 3, right? One logarithm with a base of 3 here. Okay, and here's my fraction bar, because I can see there's a positive and some negatives. So my positive is x to the 1/4, which again, I could write that as the 4th root of x, right? Just like we've been rewriting them before. And then my 2 negatives mean I'm going to put both of these in the denominator. I have 2 as a power on 5. So 5 squared times. And then I have x plus 1 with a 10 power. like so. Okay, so we can simplify that. Log base 3 of 4th root of x over 25 x plus 1 to the 10. Okay. Next, let's talk about expanding. Let's expand the logarithms now. So I have one logarithm, and the goal is, okay, the one logarithm is too complicated. I want to split it up into as many simple pieces as possible. All right, fine. So I have two modes. I have the split up mode and I have the pull out powers mode, right? It's exactly the opposite of this, where here I bring powers in and I mash. So over here, just the opposite. I separate, bring powers out. Okay? So first, I notice the multiplication, no denominator. So I'm going to have two logarithms. And I rewrote the radical as an exponent. Instead of the 5th root of y, it's y to the 1/5. So then I finish up. I have 4 ln of x plus 1/5 ln of y. Okay? Next I've got 3 pieces, right? So let's go ahead and just jump straight to it like we've been doing. We know the steps. I've got to split it and bring the powers out, right? I can see that I'm going to have 3 logarithms. So that's what I'm going to do. I'm going to have an ln with an x in it. I'm going to have an ln with a y in it. And I'm going to have an ln with z in it. The x comes from the numerator, so he should stay positive. No power, so I'll leave that alone. The y is from the numerator, so he should be positive, but there's a 3 power now. So I pull the 3 power out. And then lastly, the z is in the denominator of this, so it should have been negative, and a square root is a 1/2 exponent. Okay? So practice it a little bit, and you can sit here and just hash them out in one step like that. Okay, let's finish up with this last one here. Again, I've got 3 pieces, so I'm going to split it into 3 logarithms. I'm going to have the log base 5 of x, right? And then the square root is a 1/2 out in front, because that's the power I bring out. Now both of these next ones are in the denominator, so minus log base 5 of 25 and minus 3 log base 5 of y, right? I brought the power out. Both of them are negative because they came from the bottom. Pay extra careful attention to the ones that have just numbers. They're going to expect you to simplify as much as possible. And if you can do the log base 5 of 25, you have to do it. So that means I really should be writing this, because the log base 5 of 25 is 2. Okay? All right, guys. I hope this helps you with your understanding of the properties of logarithms.